Welcome back to G Fun Facts Online. Today, we are not just talking about a faster computer, we are talking about a rupture in the timeline of technological history. We are talking about a number so large that the human brain refuses to contextualize it, and a chip so advanced it has forced physicists to debate if we are living in a multiverse. We are talking about Willow. In late 2024, Google quietly released a paper that didn't just move the goalposts, it dismantled the stadium. They revealed a new quantum processor named Willow that performed a specific calculation in under 5 minutes. If you tried to do that same calculation on the Frontier supercomputer, currently the most powerful classical machine on Earth, a machine that fills a warehouse and consumes enough electricity to power a small city, it would not take 5 minutes. It would take 10 septillion years. Let that sink in. The universe is 13.8 billion years old. If you started this calculation at the moment of the Big Bang, on the fastest supercomputer humanity has ever built, you would still be less than 0.1% finished today. But here is the twist. That speed is actually the second most interesting thing about this announcement. The real headline, the one that has engineers popping champagne corks, is about error correction. For the first time in history, we have witnessed a quantum chip that gets better the bigger it gets. This is the story of the Willow Paradigm. To understand why this is such a monumental shift, we have to look under the hood. We need to shrink ourselves down to the atomic level and look at the anatomy of this machine. Willow is a 105-qubit superconducting quantum processor. If you look at it with the naked eye, it looks like a standard computer chip, perhaps a bit more intricate. But inside, it is a landscape of artificial atoms. Unlike early quantum experiments that trapped individual ions or photons in a vacuum, Willow uses transmon qubits. These are macroscopic circuits printed right onto a silicon wafer, made of superconducting materials like aluminum or indium. When you cool these materials down to near absolute zero, we are talking 20 millikelvins, which is colder than deep space. They lose all electrical resistance. Electrons pair up into what are called Cooper pairs and flow effortlessly. The magic happens at a specific point on the circuit called the Josephson junction. This is a non-linear inductor, a tiny barrier that the electrons have to tunnel through. This barrier turns a simple circuit into a quantum object with distinct energy levels, representing the zeros and ones of quantum information. But Willow has a secret weapon that its predecessors didn't have, or at least didn't have to this degree of refinement. It uses tunable couplers. Imagine a room full of people trying to solve a math problem. If everyone is shouting at their neighbors constantly, no work gets done. That is crosstalk, and it kills quantum calculations. In previous chips, the qubits were often statically connected. They were always talking. Willow's tunable couplers act like soundproof glass partitions that can be raised or lowered instantly. When the chip needs 2 qubits to interact, the coupler snaps open. When they need to be isolated, it shuts tight. This seemingly small engineering detail is a massive reason why Willow works. Now we arrive at the Holy Grail, the break-even point. The concept of below-threshold error correction. This is the hardest concept to grasp, but it is the most vital. Quantum states are incredibly fragile. A stray photon, a tiny vibration, a fluctuation in temperature, any of these can cause decoherence, turning your precious quantum data into random noise. For 30 years, the rule of physics was, more qubits equals more problems. If you have 50 qubits, you have 50 sources of noise. If you build a chip with 1,000 qubits, the noise becomes a deafening roar, and the computer becomes useless. To fix this, scientists came up with quantum error correction, specifically something called the surface code. The idea is to weave many physical qubits together to form one single logical qubit. It is like a phalanx of soldiers protecting a king. The physical qubits check each other for errors using parity checks, spotting mistakes without actually looking at the data, which would collapse the quantum state. The theory predicted that there was a threshold. If your physical qubits were bad, adding more of them to the phalanx would just create more confusion. But if your physical qubits were good enough, if they were below a specific error rate, then adding more of them would actually suppress the noise. The larger the group, the safer the information. Until Willow, no one had ever crossed that line. We were always on the wrong side of the curve. Google has now proven that by moving from a distance 3 code to a distance 5 code, essentially making the logical qubit larger, the error rate dropped exponentially. They cut the errors in half. This is the engineering inevitability. It proves that we can now build arbitrarily reliable quantum computers simply by building larger chips. We don't need magic physics anymore. We just need better engineering. Let's return to that 10 septillion number. What exactly was Willow doing that was so difficult? The benchmark is called random circuit sampling. It is a computational stress test. Imagine throwing a pebble into a pond. You can easily predict the ripples. Now imagine throwing 105 pebbles into the pond at the exact same instant. The water becomes a chaotic, interfering mess of peaks and troughs. Now take that image and move it into a multidimensional mathematical reality called Hilbert space. Willow runs a random sequence of operations, scrambling the information across its 105 qubits. This creates a highly entangled state. At the end, it measures the system, producing a string of zeros and ones. Because of the quantum interference, the waves canceling and amplifying each other, some strings are slightly more likely to appear than others. The task is to sample from this probability distribution. For Willow, this is natural. It is just doing what quantum mechanics does. It is like the water in the pond. It doesn't need to calculate the wave physics, it just waves. But for a classical computer like Frontier to simulate this, it has to track the probability of every single possible state. With 105 qubits, the number of possible states is 2 to the power of 105. That is roughly a 4, followed by 31 zeros. To store the state of this chip in classical computer memory, you would need more hard drives than there are atoms in the solar system. Frontier cannot store it. It has to try and calculate it on the fly, and that is why it takes 10 septillion years. This brings us to the controversy. The philosophical firestorm. When the results were released, Hartmut Neven, the founder of Google Quantum AI, made a comment that made waves far beyond the physics community. He suggested that Willow's speed lends credence to the notion that quantum computation occurs in many parallel universes. He is referring to the many worlds interpretation of quantum mechanics. The logic goes like this. If Willow is performing a calculation that requires more information density than exists in our entire observable universe, where is that calculation happening? The many worlds view suggests that the universe is constantly branching. In one branch, the qubit is 0. In another, it is 1. The quantum computer, according to this view, harnesses the computational power of these parallel realities, interfering them back together to give us an answer in our timeline. Now, to be clear, this is highly controversial. Many physicists, like Scott Aaronson, argue that we don't need parallel universes to explain the math. They say the state space is just a mathematical abstraction, not a literal set of ghost worlds. But regardless of your philosophical stance, Willow has forced us to confront the fact that we are manipulating information in a way that classical physics simply cannot account for. This achievement has also intensified the race between Google and its main rival, IBM. These two giants represent two different philosophies. Google is pursuing a fidelity-first approach. Their goal, as proven by Willow, is to prove the physics of error correction first. They are happy to have fewer qubits, as long as those qubits are high quality enough to cross the threshold. They are playing the long game for a fully fault-tolerant machine. IBM, on the other hand, has taken a utility-first approach with their Eagle and Heron chips. They are scaling up the number of physical qubits much faster, reaching over 1,000 qubits already. Their strategy relies on error mitigation, using software to guess and subtract the errors, rather than full hardware correction. They want to get machines into the hands of customers today. However, the industry consensus is shifting. With Willow, Google has shown that the path to the endgame, the computer that can break encryption and design drugs, must go through error correction. IBM knows this and is adjusting their roadmap, but Willow has given Google a significant lead in the physics, if not the qubit count. So when does this actually change your life? When does Willow cure cancer? The random circuit sampling benchmark is impressive, but it is synthetic. It doesn't calculate taxes or route traffic. The first real-world application that everyone is waiting for is in chemistry, specifically simulating the FeMoco molecule. This is the active site in the enzyme nitrogenase, which bacteria use to turn nitrogen from the air into fertilizer. Humans do this with the Haber-Bosch process, which consumes huge amounts of energy and emits massive CO2. If a successor to Willow could simulate FeMoco, we could learn how to produce fertilizer at room temperature, potentially slashing global carbon emissions by 1 or 2% overnight. That requires scaling up from 105 physical qubits to likely millions to create enough logical qubits. But thanks to the Willow paradigm, we now know that scaling up will actually work. Then there is the darker side, encryption. Shor's algorithm is a theoretical method for quantum computers to factor large numbers, which would break RSA encryption, the lock on the internet's front door. Google estimates Willow is at least 10 years away from having the scale to do this. But intelligence agencies are already operating on a store now, decrypt later basis. They are harvesting encrypted traffic today, waiting for the son of Willow to arrive in the 2030s to unlock it. In conclusion, the announcement of Willow is the end of the beginning. For decades, quantum computing was a field of if. If we can control the atoms. If we can reduce the noise. With Willow, the if has become when. The transition from scientific discovery to engineering challenge is complete. We no longer need to discover new laws of physics to build a supercomputer. We just need to build better wiring, better fridges, and cleaner chips. The clock is no longer ticking, it is sampling, and for the first time, we are winning the race against the noise.